Nancy. In this, we'll be exploring the closure properties of context-free languages, having theoretical insights and implementations. So let us start. Introductions to CFLs. In this presentation, we will look into context-free languages and their closure properties. Understanding these properties is crucial for various applications in compilers, formal languages, and automata theory. In this, we will explore more about theoretical insights and their implementations in computer science. Definition of CFLs. Context-free languages are defined by context-free grammars and can be recognized by push-down automata. They play a vital role in syntax analysis and are essential for programming languages. Understanding their structure allows us to analyze their closure property effectively. Closure property overview. Closure properties refer to the ability of the class of languages to remain within the same class after certain operations. For CFLs, these properties include union, concatenation, and cleanse star theory. Understanding these operations is essential for theoretical analysis and practical applications. Union of CFLs. The union of two context-free language is also a context-free language. This property allows for the combination of two different languages constructs, enhancing the expressiveness of CFLs, which is particularly useful in designing complex programming languages features. Concatenation of CFLs. The concatenation of two context-free languages results into another context-free language. This property is significant in language processing, allowing for the sequential combination of language elements, which is commonly used in programming structures. Cleanse star operation and theory. Applying the cleanse star operation to a context-free language produces another context-free language. This means that the operation enables the repetition of language constructs, which is essential in defining patterns and structures in programming and formal languages. Intersection with regular languages. The intersection of a context-free language with a regular language is context-free. This property highlights the versatility of CFLs and their ability to interact with simpler language classes, expanding their applicability in practical scenarios. Transition diagram showing the insertion of CFLs. However, when we look into the intersection of two context-free languages, it is not necessarily context-free. This limitation possesses challenges in language designing and parsing, emphasizing the need for careful consideration in theoretical and practical applications. Implementation of the complement of CFLs. The complement of a context-free language is not guaranteed to be a context-free. This property raises an important questions regarding the boundaries of context-free languages and their limitations, particularly in formal languages of the theory. Applications in computer science using automata theory. Understanding the closure properties of context-free languages have significant implementation in compiler design, syntax analysis, and natural language processing. These insights enable the creation for more efficient algorithms, robust language, and parsers. Future directions in automata theory using CFLs. Future research may focus on exploring the limitation and extensions of context-free language, particularly in relation to context-sensitive languages. This exploration could yield the new theoretical frameworks and practical applications in various domains. Pushdown automata. What is a pushdown automata? It is nothing but a PDA which can be defined as a queue, which is the set of the states, sigma, which is the set of input symbols, tau, which is the set of pushdown symbols, Q naught, which is the initial state. Z is also a pushdown symbol, which is in the full stack. F is the set of final state. Sigma, which is a transition function that maps the Q into epsilon U union of the whole tau into Q into tau star. In this given state, we can see that the PDA will read the input symbol and stack symbol on top of which the stack is present to move to a new state and change the symbol of the whole stack. Pumping lemma. The pumping lemma says that for any regular language, there is existing a constant such as that a string in which a length has at least to be split into three substrings, which is can be non-empty also, such that the strings are also in it. This process, repeating of zero or more times, is known as pumping. Parsing algorithm. A compiler checks whether or not it has a tokens or group of lexical classifiers which are classified accordingly to the syntactical rules which is having the language. This is done by the classifier itself. The parser receives a string of tokens from the lexical parser and checks that the string must be having a native language. It detects and reports any syntax errors and generates a parse tree from which it intermediates code and can be generated. For example, in the diagram we can see we have a parser which goes down with the token, which is a lexical analyzer which analyzes the text, which then goes to a symbol table. Symbol table goes to a parser or rest of the front end. Using the front end, it can detect whether it's a parse tree or not. Again, this rechecks with a token, which is nothing but which is coming from a source program. In conclusion, we will see that exploring these closure properties of context-free language provides valuable insights into the structure and capabilities. Understanding these properties is essential for advancing theoretical languages and enhancing practical applications in computer science. Thank you for watching today. That's all for today in Theory of Automata. Thank you.